Okay, we're going to take a look at section 14.3, which covers a variety of topics which are all connected, but they begin with Pythagorean's theorem. And we're going to formally look at it. I believe we've kind of looked at it before, but let's start with our given. If we are given a right triangle, with a right triangle, let's make sure that we know the various parts and pieces. On a right triangle, we have the right angle, and we've talked about this in the past with congruent triangles. The 90 degrees is the largest side, so it produces the 90 degrees is the largest angle, so it produces the longest side called the hypotenuse. Okay, this is always the longest because it's across from the largest angle. And the other two angles produce sides across from them, which we can call legs, or we can call sides, either one. And so you may see it written this way. So if I give you a right triangle, and this time I'll call this angle A, angle B, angle C. The side that is produced by angle A, the side that produces across from it, we call lowercase a, lowercase b, and we'll call the hypotenuse lowercase c. Remember, capital letters represent vertices or points. Lowercase letters represent lines or line segments. Then Pythagorean's theorem named after Pythagoras. Pythagorean's theorem states that if triangle ABC is a right triangle, having a hypotenuse of C, then the sum of the squareds of the sides, a squared plus b squared, must equal the hypotenuse squared. So what we're going to do is take a look at a few of these and practice it straight out, and then we'll take a look at the converse. So let's first do a visual. As you know, I always like starting, especially with children, starting with a visual so that they get an idea of what we're talking about as we introduce some of this vocabulary. So let's just show how this works. Let's say I have a triangle A where side A is 4 units long, side B is 3 units long, and side C is 5 units long. And let's just see how this works. Okay? So if this is a right triangle, then we should get that by Pythagorean's theorem, a squared plus b squared should equal c squared. So we would always set it up, especially when you're talking with children. Make sure you show them, have them substitute in the values, and then we end up with 16 plus 9 does indeed equal 25. So 25 equals 25. And so that's how the Pythagorean theorem can work. Okay? And that's what we call a Pythagorean triple. I want to give you another Pythagorean triple. Let's go this way. Here's our right angle. You cannot assume it's a right angle unless you are told it's a right angle. In this case, I use the symbol. I'm going to tell you that one side is 5 units long, so not drawn to scale. One side is 12 units long, and the hypotenuse is 13. So is this a right triangle? It will be if 5 squared plus 12 squared equals 13 squared. 25 plus 144. 13 squared is 169. So sure enough, you'll notice that these are nice whole integers. They're nice whole numbers. They're nice numbers. So those are what we call Pythagorean triples. Okay? So a 3, 4, 5 triangle, a 5, 12, 13 triangle, we call those Pythagorean triples because they produce nice whole numbers. So there's some other Pythagorean triples we may run across. But kind of wanted to show you that. So let's say, for example, now we're going to try some. I'm going to give you guys a word problem. Move off of the visual. So let's do this. Let's say a ramp from a sidewalk is 7 feet long. Okay. To a doorway. Now, let's say the base of the ramp is 5 feet from the building. The base of this ramp So what I'd like to know is how high off of the sidewalk is the door. And oftentimes, as you know, students, including some of you, get very anxious as soon as we have words. So we want to annotate it, and we want to look at drawing a picture to have us help. So right now I have that the ramp is 7 feet long from a sidewalk. All right, so if I have my sidewalk along here, I have a building along here. Here's my building. I'm not fancy, it works. Here's my sidewalk. And I have this ramp. So here's this ramp. And I know this ramp is 7 feet long. The base of the ramp is 5 feet from the building. So that must mean that from the edge of the building to the base, the bottom part of my ramp is 5 feet. Now, assuming that the building is vertical, and in this case, we can assume that our buildings or trees or people, towers, are all vertical from the ground up. How high off of the sidewalk is the door? So it comes into the door here. So I'm just going to call this X. Okay? Or I could have called it Y for going vertical, or I could have called it A or B, because you'll notice we produced a right triangle. So by Pythagorean theorem, we should get that x squared plus 5 squared equals 7 squared. By solving this problem, keeping equal signs lined up to help with organization, x squared is the same as 49 less 25. So x squared is the same as 24. Solve this by taking a square root. Now I'm just going to refresh our memory here. That would be the same as the square root of 4 times 6. I looked for a perfect square, that way I could take that out. The square root of 4 is 2. 6 does not contain any perfect squares as factors. So here would be the actual length if I want the exact value. Or for an estimate, we can say the square root of 24 is approximately 4.9 feet. And that's how high off of the ground our door would have to be in order to accommodate that 7-foot ramp. All right, so it's kind of looking at what we're given and going from there. So hopefully that helps a little bit with Pythagorean theorem. I want to give you a different scenario. So let's take a look at another example. All right, and there's all kinds of word problems. There's all kinds of things out there that we use Pythagorean theorem for. We use it a lot in geometry with actually building structures. Okay, so right now we're just looking at the mechanics of this. So here, let's give you another one. Let's take a triangle. And this time I'm going to give you that it may not be equilateral. In fact, it's not. I'm going to give you that triangle ABC. So right now it is not a right triangle. BC is 17 units long and AC is 16 units long. And what I'd like you to do is actually twofold. The first part, find the altitude of triangle ABC. Okay? But I'm going to give you another piece to help you out here. Given that point D is the midpoint of line segment AC. So I'm going to put in the altitude there. Now my drawing's a little off, but I'm going to estimate. So the midpoint is roughly right about here. It's a little bit off, but I'm going to call that D. Of course, we now know how to construct a midpoint. The altitude is also called the height. But the altitude goes from any vertex to the opposite side and is perpendicular to the opposite side. It is not always the midpoint. I'm just giving you that in this case it is the midpoint. So because it's the altitude, we know that it is going to be perpendicular to the opposite side, so we've now formed a right triangle. Since it's also the midpoint, we now know that side AC is 16. Therefore, half of it is here and half of it is here, so each of those segments is 8. And so now what I'm going to do is pull this triangle apart, and I'm actually going to take this one large triangle and pull it apart into two smaller triangles, and just analyze using one of these triangles. I now have a right angle, point B, point C, point D. This is 8 units long. This hypotenuse is 17 units long. And in this case, I'm looking for side C, which is across from angle C, and I want the altitude. Well, because it's a right triangle, then I know that the sum of the sides squared. So C squared plus 8 squared will equal the hypotenuse squared. So I don't have to get locked into the letters A, B, and C. I need to know what they represent. They need to know these are the side lengths. And now the rest is some arithmetic. 8 squared is 64. 17 squared is 289. Subtract 64 from both sides. If we subtract 64, we get 225. And the way to find C now, if I take the square root of 225, I get C equals positive or negative 15. But since we're talking about how high or how tall or a length of a side, we've got to have it the positive value. Okay, so there's all kinds of ways to incorporate Pythagorean theorem. It doesn't have to be given as a right triangle right away. Now, as I started off, this example was going to be twofold. The first part was to find the altitude. And the second part, so I'm going to call it part B, is find the area of the original triangle. Find the area of triangle ABC. Well, since it's a triangle, we already know how to find that. We know, always start with what we know. Area is the same as 1/2 base times height. Area equals 1/2. Well, the base and the height are the sides that are always perpendicular to each other. So in this case, our entire length, remember, was 16. So our entire base is 16. We now found what that altitude is, or that altitude or height is 15. And so we are ready. Area is the same as 8 times 15. So area is 120. We don't have any units, so we'll go back and recall that that's then square units since it's area. And so I do recognize that in our class we have done some of the Pythagorean theorem. There's a lot of ways to prove the Pythagorean theorem. We are just using it, but it is an interesting example, an exercise to go through as how to prove it. So you can look online in a variety of ways. So now that we have the Pythagorean theorem, which always starts with the right triangle, let's look at its converse. All right, so I know I just wrote this down, but I just want to do this to refresh your memory on converse. Pythagorean theorem says if a squared plus b squared equals the longest side squared, then triangle ABC, I just did it the other way around. Sorry guys, I just did the converse. The Pythagorean theorem says if triangle ABC is a right triangle, then a squared plus b squared, the two sides squared, must equal the hypotenuse squared. Well, if you recall from the last course, the first part of the book, a converse says to take your hypothesis and conclusion and switch places. So the converse to the Pythagorean theorem, well, we have to take the conclusion and make it the hypothesis. So if a squared plus b squared equals c squared, which would have to be the longest side, then triangle ABC is a right triangle. Okay, so let's take a look and see how we might be able to use that. So let's do a couple of examples. Let's, for example, determine whether the triangle having the following lengths, the lengths given, determine whether or not it is a right triangle. All right. So the first triangle we're going to take a look at has sides 4, 9, and 12. Well, if this is a right triangle, we would have to check to see whether 12 is, this would have to be the hypotenuse because it's the longest side. All right, that one just dried out on me. Okay. So we would have to use the 12 as a hypotenuse if it's a right triangle. So we need to check, is one side plus another side equal to the longest side squared? So is 4 squared plus 9 squared equal to 12 squared? Is 16 plus 81 the same as 144? On the left side we get 97. On the right side we get 144. So those are clearly not equivalent. Therefore, this is not a right triangle. And if you remember from a couple chapters back, it is a triangle. Because if I add up any two sides, it should be longer than the third side. So this is a triangle. It just is not a particular right triangle. So let's say I give you another triangle. Let's say I give you having sides 2, 3, and the square root of 13. If you're not sure what the square root of 13 is, of course we could put it in a calculator, but we could also check, because we know that 3 squared is 9, and we know 4 squared is 16. So 13 falls somewhere between 9 and 16. So my answer's got to be somewhere between 3 and 4. And so it looks like the square root of 13 is the largest of the three of them, because it's bigger than 3, but it's less than 4. And so we want to check. Is 2 squared plus 3 squared equal to the square root of 13 squared? Is 4 plus 9 equal to, well, if I square a square root, they undo each other. So we end up with 13 equals 13. Since this is a true statement, this is a right triangle. Because Pythagorean theorem worked. So that's how we can use the converse of the Pythagorean theorem. We're given the sides, and if we're given the sides and this ratio, this equation works, then it is indeed a right triangle. Okay. And so now that we've talked about some right triangles, I want to review a little bit of trig with you with some special right triangles. And just as more of information for when we might look at some other figures and polygons. So we do have a couple of special right triangles. And we can use Pythagorean theorem to verify that these ratios I'm going to give you are indeed accurate. So what I'd like to start with is we have only two. We have two special right triangles. Okay, so the first one I'd like to look at is an isosceles triangle. It's an isosceles right triangle. Isosceles, remember, means that two sides are the same. So if I give you two sides that are congruent, if the two sides are congruent, then the two angles are congruent. So both of these base angles would be 45 degrees. Since the sides are the same, they would be x and x, and by Pythagorean theorem, because it's a right triangle, I can find the third side by taking a squared plus b squared. That's going to give me c squared. So if I add these together, okay, that third side, this would give me a 2x squared equals the third side. If I take the square root, I get x, because the square root of x squared is x. times the square root of 2. So we have this special ratio that says, what's really nice about a 45-45 is if we know what the two sides are, all we have to do is multiply it by root 2. So sometimes you might see it this way. You may have seen this in high school this way. If this is a 45-45, 45 degree, 45 degree, they are then in a 1-to-1 ratio because they're the same. And again, if I do Pythagorean theorem, 1 squared plus 1 squared would give me 2. That's going to be the third side. When I take the square root of it, I get a root 2. So some like pictures. Other people might like seeing it this way. If it's an isosceles right triangle, if it's an isosceles, and I know that I have a 45, 45, 90 triangle, some might organize it this way. Well, since both of these are the same, 45 degrees, I could call that x to x root 2, which is what I did with this picture. Each of the sides across from 45 is x. The side across from the 90 is x root 2. Or you could reduce them all, and this is a 1-to-1 to root 2 ratio. So you might say, well, why do I care? Well, how can that help me? Well, let's say, for example, I know you could do Pythagorean theorem. I know you can because we just did it. But let's say I give you this triangle, and right now I tell you that this is 45 degrees. Well, you automatically know the other one's 45 because the sum of these three have to add up to 180. Well, since both of those angles are the same, and let's say I give you that this is 5, well, I now know both legs have to be the same. And as soon as I recognize that it's 45, 45, as soon as I recognize both of these are the same number, I take that number and multiply by root 2. So that's how I could find the hypotenuse, just by setting up the isosceles triangle. Conversely, let's say I gave you this picture. And I give you, this is 45, 45, 90. And I give you that the hypotenuse is 3 root 2. And I want you to find the two side lengths. Well, again, since they're in a 1-to-1 to root 2 ratio, since they are in a x root 2, I've now figured out what x is. Since I have 3 root 2, that means each of these sides must be the number 3. And so that's how we can use that special triangle. But we have a second special triangle. The first one's isosceles, 45, 45, 90. The other special triangle is a 30, 60, 90. Oh, my pen's a little thick. Sorry about that. That's a 30 degrees, 60 degrees. Here, I'll draw it a little larger. That's 30. That's 60. If you don't like that, I could also do it this way. 30, 60, 90 degrees. Depends on how you visualize it. I'm going to do the same thing we did over here. Well, one thing to notice about a 30, 60, 90 is the smallest angle will always produce the shortest side. So this 30 degree angle produces the shortest side that I'm going to call 1x. And you'll need to trust me for now. You can do some investigation as to why. But the hypotenuse is the longest side, and it's across from the largest angle. So what's really cool is if the shortest side is x, the longest side is twice x. And of course, we could calculate the third side again by Pythagorean theorem, and we could calculate it by saying, well, this would be the same as b squared is the same as 4x squared. Bring that x to the other, from the left to the right side. So b squared equals 3x squared. And as soon as I take the square root, I can pull an x out, and I'm left with a root 3. So the shortest side would be x, the longest side would be twice that, and the middle side would be x root 3. Because the square root of 3 is between the number 1 and 2. 30 degrees goes with the shortest side, 60 degrees produces the middle length side, across from the 90 degrees always produces the hypotenuse, the longest side. So you could say, okay, the ratio across from the 30-degree angle is 1x. The hypotenuse is always twice that. The middle number is the square root of 3, which falls between 1 and 2. Or you could write it this way and say 30 degrees is x, 90 degrees is twice that, 60 degrees x root 3. Or 1 to 2 to the square root of 3 ratio. So looking at similar type problem, let's say, for example, I give you, here, we'll do this. I'm going to give you this rectangle, and I would like you to find the length of the diagonal. So I'm just going to draw, I'm just freestyling it, draw that diagonal in. And I am going to tell you that here's my right angle. Of course, they're all right angles because it's a rectangle. I'm going to tell you that this height is 2 and this base is 2 root 3. So right now I may recognize it's one of our special triangles. But I'm going to go ahead and for now give you this and tell you that this angle is 30 degrees. So we would know that the sum of any angles of a triangle add up to 180. And so this one would have to be 60. And now you'll recognize, I hope, that that's our 30, 60, 90 ratio. So what I personally do is I always locate my 30-degree angle. Now, you could do Pythagorean theorem. Of course, you could extract out the triangle. Of course, it will always work if I take and use Pythagorean theorem, since I gave you the two sides. And you can always find that third side. But I'm trying to get you to use the special triangles, so you may recognize you have a 30 degree, you have a 60 degree, you have a 90 degree. We know that they're in the ratio of x, x root 3, and 2x. So all we need to do is figure out what the x is. And the x represents the shortest side. The x represents the side opposite the 30 degrees. So if I look at the side opposite the 30 degrees, that number is 2, which means the other side better be 2 root 3, which it is. Therefore, the hypotenuse would be 2 times 2, or in our case, 4. So the length of that hypotenuse is 4, which means the length of that diagonal is 4. Okay. And then I kind of threw this one in together. I want to see what you'll do with this. Let's see. So, look at this example. Okay. Give you a minute to set up. Give me a minute here to erase. I think the black shows up well for your end. Hopefully you don't see the shadow I do here with the black on the whiteboard. It's a little cloudy, but I think it'll be okay. Okay. So here's what I might ask you. Sort of put it all together. I'm going to give you a triangle. And I'm going to tell you that this base, the entire base, is x units long. I'm going to tell you this one base angle is 45 degrees. The altitude or the height is y. And all I'm going to tell you is that this is 2 root 2. So what I would like you to do is, based on that triangle, based on given information, I would like you to find the values of both x and y. So what I notice is I gave you that y was an altitude. So I gave you the fact that y is an altitude, which means I've now given you the fact that I have a right angle within that triangle. So if I extract that piece only, if I just extract the right side of this triangle, and I know this altitude is y, I know this angle is 45, I now know because it's an altitude I have a right angle, and I know the hypotenuse is 2 root 2. So let's figure it all out. Well, if this is 45, I know the other one's got to be 45. And so now I've created a 45, 45, 90 degree triangle. And in a 45, 45, 90, we know that we have a ratio of x to x to x root 2. So we also now know that in this particular problem, the side opposite the 90 is 2 root 2. So we've now figured out what x is. We now figured out that x is 2 and x is 2. So that means that both of these sides have to be 2 units long. So the altitude is 2 and this piece is 2. So I've now figured out what y is. And now let's go back and figure out what x is. All right. Well, if I go back and figure out what x is, and I guess I would have to give you the fact that it hits the midpoint, or I'd have to give you the fact that this triangle is isosceles. So in this particular case, now that I know that one side is 2, and I know that this piece right here is 2, and if I've told you it's a midpoint, this piece would be 2, and therefore x is 4 units long. Okay. So we're going to move from Pythagorean's theorem and our special triangles to what's called the distance formula. And the distance formula is 100% based on Pythagorean's theorem. So it's a nice way to introduce it by using what you already know and use the Pythagorean theorem. So let's take a look at the distance formula, which will then lead us directly into circles. Believe it or not, we're going to go straight from triangles into a circle. So if I'm on a plane, I'm on a 2-dimensional surface. Okay, so what I'm going to give you is I can pick any 2 points on a graph. To make it probably the easiest to understand, and in a pre-cal class we'll go farther. But let's pick any 2 points in this first quadrant. So I'm going to call this first point x1, y1. And I'm going to pick a second point, and I'm going to call it x sub 2, y sub 2. All right, so now that we have our 2 points, and these can be any 2 points, what I'd like us to do is our goal is to find the distance between these 2 points. So here's the distance that I'm going to call. Whoops, a little crooked there, I apologize. Here's the line segment that I'd like you to find the distance of. Now because we put this on an xy plane, everything is rectangular. So what we actually have is, notice because it's on the coordinate plane, I can put this, it's on the rectangular plane, so I can make a right triangle out of this because it's on the rectangular plane. So now that I have a right triangle, let's find the coordinates of this other point. So we've got to ask ourselves, well, in the x direction, how far over along the x-axis have we traveled to get to this value right here? Well, here's our first x, and we called it x sub 1. You'll notice this point lines up exactly with the point that has the x-coordinate of x sub 2. Similarly, how far in the y direction have we gone if we've gone this far? We have not gone all the way up here to y2. You'll notice we've gone as far as whatever this value is here. So I can call this point x sub 2, y sub 1. And then what we can do from here is let's figure out how long each of the sides are. So if I go from the first point to the second point in the x direction, well, think about any number line. How do I figure out how far apart 2 numbers are? I come up with their difference. If I give you a number line and I ask you how far apart is the number 2 from the number 10, you could say, well, if I start at 10 and subtract 2, that tells me how far apart they are. So in this case, the difference between the x values will tell me how far apart they are. So this entire distance is x2 minus x1. Similarly, in the y direction, how far apart are these y values? Take the larger value and subtract the smaller value, or just find the difference between them. So now we have our 2 side lengths. So the question is, how do we find this distance? I'll just call it d for distance. Well, we use Pythagorean theorem. Since this is a right triangle, we're going to use Pythagorean's theorem. And so normally we say a squared plus b squared equals c squared. Well, we called one side the difference of the x's, so we're going to square that. We called the other side the difference of the y values, so we're going to square that. And that's going to give us our distance squared. How do we solve for d? We take the square root. So if I take the square root of the right side, I get d. If I take the square root, those are separate terms, so I cannot do them individually. I have to keep it all together. I end up with the square root of the difference of the x's squared plus the difference of the y values squared, and that's what we call the distance formula. So some of you may say, wait a minute, it's kind of like when we did slope and we did the difference of the x's and the y's. Yes, because we're still talking about 2 points on a plane. Okay, so let's take an example of using the distance formula. So normally, if we were in class together, I would randomly ask two different students, and I might say, I might pick a name and might say, okay, David, give me a point that is in the second quadrant. So I'm reviewing the quadrants, and my student might say, okay, I'm going to pick the point -2, 6. And this is a great opportunity if you have a shy student in class to select them by just saying, okay, Jessica, pick a point that's in the fourth quadrant. And while she's first recognizing, oh no, my name's been called, you can be talking about, now everybody remember where the quadrants are, quadrant 1, 2, 3, 4. So Jessica, give me any point at all in the fourth quadrant. And you've just given her time to create a number in case she forgot it. And I'm just going to choose, and I'm going to pretend that my student chose 1, -4. So 1, 2, 3, 4, 5, 6. Not exactly drawn to scale, but we get the idea. Now, you will automatically get some students who want to draw the triangle and figure it out, and that's fine. I'm just going to draw this for a visual. We want to find that line segment. We want to find the distance between those 2 points. So if I go straight to my equation, the distance formula would say the square root of, well, I have to subtract the x's. So you have a choice. You can either say -2 minus 1, or it's the same line segment if you go 1 minus -2. And it will not matter because whatever we get, we're going to square. So as I read from left to right, I'm going to call this point my first point and this one my second point. So if I say x2 minus x1, I'm going to square that. Then if I take the y value from the second point of -4, subtract the y value from the first point of 6, and I'm going to square that. Be careful. Negative minus a negative makes that a +2. -4 minus 6 makes that a -10. So I believe we get 3 squared plus -10 squared. So we end up with 9 plus 100, or 109. So that's the distance between them. And oftentimes I'll get students that tell me, do I have to memorize this formula? And I tell them every single time, no. Because if they go and they are recognizing that I'm doing this problem, and they recognize that this actually creates, it's a little better on graph paper, but you'll notice that what this is creating is a right triangle. Some students would rather logically figure out that I know exactly where this corner is. I went left 2, down 4. I went left 2, down 4. So I'll get a student who will logically deduce that, look, they can just count. And they can tell me that from -2 to +1 is 3 units. And in the y direction, from -4 to +6 is 10 units. And then they just ask me, well, can't I use Pythagorean theorem and say a squared plus b squared is going to give me my c squared, or my distance, if you prefer c squared. I get a 9, 100. 109 is c squared, so c is the square root of 109. So either way, we get the same thing. All right? So it's nice to have a formula, but make sure the concept is there, and it's nice for them to be able to show you how they know that that works. Okay. And so as I mentioned before, I said, well, if we can do distance formula, we can find the equation of a circle. So we have done Pythagorean theorem. We have finished the distance formula. Let's take a look at how those two things relate to, well, they're identical, but how they relate to the equation of a circle. So again, one of the things that oftentimes teachers do is they just tell you the formula. And a lot of times it's harder to understand the formula if you have no idea where it came from. So a nice way to develop this and develop the equation of a circle is to start with a circle at the origin. Circle with center at the origin. So I'm going to put a circle, and I'm just going to freehand a circle, okay? And I'm going to freehand a circle. I'm going to put the center of my circle, and again, I'm sort of sketching it. I'm getting the freehand. I think you guys get the idea of this. I'm going to choose to make the center of my circle the point 0, 0. I'm going to put this on the XY plane. And a nice way of showing students, instead of memorizing, go off of what we just did. Again, let's pick any point that's on this circle. Because we know points are made up of X's and Y's. I'm going to choose, it really does not matter where on the circle, I'm just going to pick the first quadrant, and I'm going to pick this point as XY. And how did I get to that point? Well, you may say, if I would explain, you went to the right X distance, and then you went in the Y or up Y distance, and guys, look at what you just made. You just created a right angle because it's on the rectangular coordinate system. But look at what else you have. The shortest distance from where you started at the center to the point on the circle is this diagonal. And if we look at the circle, that diagonal line represents the radius of the circle. So you'll notice the radius of the circle is exactly the same as the hypotenuse of the right triangle. Well, if it's a right triangle, we know that if it's a right triangle, whoops, I forgot the N, we know with a right triangle, a squared plus b squared equals c squared. Okay. One side we're going to call X, one side length we're calling Y, and our hypotenuse is also the radius of a circle. So what we have actually done is we have developed, excuse me, by simply using Pythagorean's theorem, we have come up with the equation of a circle with center at the origin. And our equation is x squared plus y squared equals the radius squared. And all we did was use Pythagorean theorem and recognize that the radius was the same as the hypotenuse. And it does not matter where on the circle you pick a point, as soon as you square your x value and your y value, even if they started off negative to imply it was in a different quadrant, you'll get the same result. So hopefully there's somebody out there saying, well, that's great, but not all circles are at the origin. So let's pick a circle with center not at the origin. And I'm just going to pick some random location where I'm going to go HK. I don't want to use XY because we're on the XY plane, so I needed to use different variables. So in the X direction, we'll go some value H. In the Y direction, we'll go some value K. So it still represents a point. So let's kind of, let's do that. I'm just, sorry, freehanding. Here's X, here's Y. And let's do this. Let's put our center, I want to make sure you guys can see it. Here, we'll put our center right here. So here's the center of the circle. And all I'm going to tell you is this center is HK. Okay, maybe it's 4 over and 2 up. Doesn't matter. All I'm going to tell you is that's the center of our circle. So if I can freehand a circle, I'm going to kind of do this. Maybe it'll be a little more accurate. All right, that's not too bad. But here's my circle that's not located with the center at the origin. But instead of memorizing a formula, let's have you come up with it. So we're going to do this. We're going to play the same game that we did on our first circle. Pick a point anywhere on your circle. All right. I'm just, so I don't run into my hand, I'm just going to go further to the right. I'm just going to pick this point right here. The reason I'm calling it XY is because it's on that XY plane, and it can represent any one of these points that are on this XY plane. And instead of memorizing, let's analyze. Let's think about how we got to that point. Well, I've gone over, I've gone up, and the shortest distance would be the hypotenuse or the radius of that circle. Again, I need to find this corner value. Well, that corner value, similar to our proof for the distance formula, how far have I come along to the right? I've passed H. I've gone all the way to X. How far in the Y direction have we gone? We've come up as far as this point here that we started with at the center. So we have come up K units. So, since we have a right triangle, I could easily do Pythagorean theorem, and I can say, of course, a squared plus b squared equals c squared. Well, how long is this in the x direction? How far is it between h and x? The only way to find that out, subtract the values. So this would be x minus h. It says to square it. How far have we gone in the y direction? To figure that out, it's the difference between those. So that's y minus k squared. And what does the c squared or the hypotenuse represent? This c squared, or I mean rather this c value, represents the radius of our circle. We're done. You're done. You just found the equation of the circle that's not at the center. We just had to shift it off of the center. So the equation of a circle with center not at the origin, just some random point, is very similar to our center at the origin, but now we have shifted away from the origin. Notice that if I started here and subtracted h, I'd be right back to 0. If I subtract k, I'd be right back to 0. So it's just a translation. X minus h squared plus y minus k squared equals our radius squared. So let's practice. Here, before I erase this, let's do the following. Let's say I give you x minus 1 squared plus y minus 4 squared equals 25. Okay, let's find the important facts. In order to graph a circle, we need to have a center point. So our center is our quote HK. Our center wants to be at 0, 0. So what would x have to be in order for us to subtract 1 from it and get 0? Our x would have to be 1. What would our y value have to be so that it would slide back or translate back down to 0? Our y value would have to be 4. We also need to find the radius so we know how wide or we know how far to open our compass. Well, we know r squared is 25. Right here, we know r squared is 25, so therefore the radius, if I take a square root, I technically get plus or minus 5, but I can't have a negative distance, so that plus or minus represents going in the positive direction 5 and in the negative direction 5. So if I were to graph this, and I'm going to sketch it. I need to start at the point 1, 4, 1, 4. There's my center at 1, 4. Then, since the radius was, quote, plus or minus 5, that means I need to go 5 to the right. 1, 2, 3, 4, 5 to the right. I'm not going negative 5, but I'm going in the opposite direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm just sketching this. In the y direction, I also need to go up 5. 1, 2, 3, 4, 5. And I would need to go, quote, minus, or in the opposite direction. 1, 2, 3, 4, 5. And then the most challenging part is going to be trying to draw your circle, connect the dots so that it looks somewhat circular. Okay? So hopefully that helps with graphing and finding the equation of a circle. And all we need is a center, all we need is a radius, and we can substitute it right into our equation. So try some of those. If you have questions, I'm wondering, okay, if you have some questions, you might have to find the radius by finding the distance between the points and give it a try. If you have any questions, of course, let me know. And so that's it for equation of a circle.